This video demonstrates the use of the continue statement in a loop. And what this program does is it determines whether a given number is prime. Let's just go ahead and play with this program a little bit. So we've compiled, and we execute, so we'll check if 50 is not prime. How about 13? 13 is prime. The program takes a little while to compute that, but that's fine. So that's looking pretty good. Now the definition of a prime number is that the number is greater than 1. So let's try a number like 1. 1 should not be a prime, but it comes up as 1 as a prime. That's not right. What about negative 1? Negative 1 is not greater than 1, therefore it's not a prime, but yet it comes up as a prime. How about another number like negative 50? So it says negative 50 is not prime. Okay, so these are incorrect results. So how do we fix this? Well, once the program prompts the user to enter an integer, collect that integer, we can immediately determine whether that number, the user num, is not greater than 1. So we'll say it's not greater than 1. And if that's the case, then we will say that prime is false. Prime is false. It's not a prime number. And I close the old program, recompile, and execute. So is 1 a prime number? Should say no. It is not a prime number. That's correct. What about negative 1? And these are not prime because they're not greater than 1. Only numbers greater than 1 can be prime. So that's right. What about 50? 50 is not prime. That's right. How about 13? 13 is prime. All right. So now the behavior is corrected, but why does it take so long to determine that 1 is not prime? Immediately after getting the user input, we do an if statement and determine that the user has inputted a number that is not greater than 1, therefore it is not prime. Therefore we could immediately output that it is not prime. But what's happening is the program is executing this for loop. And what this for loop is doing is trying all numbers between 1 and a billion to see if that number is a possible divisor of the user entered number. But we can completely skip this for loop. It's unnecessary. And one way to do that is for us to use the continue statement. And we can use that continue statement once we've determined that the number is not greater than 1, we can continue. And what the continue does is jumps to the end of the loop that the continue is within. In this case, the continue is in the while true loop. So let's take a look at that. Compile, execute, so 50 is not prime, that's fine. How about negative 1? It still took a while. Why did it take a while? Well, I forgot to save the program. So we compile the old code. Alright, well, I've saved the program. Let's compile again and execute. So if we do negative 1 as our input, then enter this if statement, set prime the flag equal to false because it's not prime, and then the continue statement occurs, which jumps the program to the while loop, and then we once again ask the user to enter an integer. So that's what's going on here. So as long as I have a number that's not greater than 1, then we'll continue to have no output to the user, which is instantly ask again, because the program will simply continue, which will bring it to the beginning of the while loop, and once again ask the user for input. That's what will happen as long as the input is not greater than 1. So for example, if we put 5, then it calculates to determine whether it's prime, which it is. Okay, so all we need to do now is add some output saying that the number is not prime when the value is not greater than 1. And then we will recompile and execute. Enter an integer, let's say 1. 1 is not prime. How about 0? Negative 3, negative 13. The program runs very quickly when determining whether a value is not prime when that value is not greater than 1, because we immediately output is not prime and then continue. It's skipping the 1 billion for loop. Thank you.